Ever thought about how a doubly linked list operates in the realm of computer science? Well, let's dive into it. A doubly linked list is a particular type of linked list where each node contains a data element and 2 pointers. Yes, you heard it right, 2 pointers. Unlike a singly linked list, which only has a pointer to the next node, a doubly linked list has an additional pointer to the previous node. This feature enhances the versatility of the list, allowing traversal in both forward and backward directions. Imagine it like a two-way street where you can move forward to the next node and also go back to the previous one without any hitches. Each node in the list is a bundle of 3 components: data, a pointer to the previous node, and a pointer to the next node. So, a doubly linked list is a dynamic data structure with each node having 3 components: data, a pointer to the previous node, and one to the next node. Now, let's delve into the basic components of a doubly linked list. At the heart of a doubly linked list are its nodes. Each node is like a tiny container holding 3 essential elements. First, there's the data. This could be anything: a number, a character, a string, or even an object from a class, depending on what you're using the list for. Next, we have 2 pointers. These are our navigational tools. One pointer always points to the previous node, while the other points to the next node. These pointers are what make the list doubly linked. They allow us to move forward and backward through the list, giving us a great deal of flexibility. But how do we start navigating the list? That's where the head pointer comes in. The head pointer is like a bookmark at the very start of our list, pointing to the first node. It's our entry point into the list and the starting point for any forward traversal. On the opposite end, we have the tail pointer. This pointer marks the end of our list, pointing to the last node. It's the final stop in any forward traversal and the starting point for any backward traversal. So in a nutshell, each node in a doubly linked list contains a piece of data and 2 pointers. The data is the information we want to store, and the pointers allow us to navigate through the list. The head and tail pointers mark the start and end of our journey through the list. Understanding these basic components is crucial to grasping how doubly linked lists work. These lists are like a chain of nodes, linked together by pointers, with the head and tail pointers serving as our start and finish lines. So, a doubly linked list is built with nodes and guided by the head and tail pointers. With the basics out of the way, we can now look at the operations that can be performed on a doubly linked list. First off, we have insertion operations. These allow us to add new nodes to our list. We can insert a node at the beginning of the list, at the end, or even after a given node. When inserting at the beginning, the new node becomes the head of the list. Conversely, when we insert at the end, the new node becomes the tail. And when we insert after a given node, the new node takes its place in the sequence, pointing to the node that used to follow the given node, and being pointed to by the given node itself. Next up, we have deletion operations. These let us remove nodes from our list. Similar to insertion, we can delete a node from the beginning, from the end, or following a given node. When we delete from the beginning, the second node, if it exists, becomes the new head of the list. When we delete from the end, the second to last node becomes the new tail. And when we delete after a given node, the node that follows the one we're deleting is now pointed to by the given node. Moving on, we have traversal operations. These allow us to move through our list, either forwards or backwards. We start from the head and follow the next pointers to move forward, or start from the tail and follow the previous pointers to move backward. This bidirectional traversal is one of the key features of doubly linked lists, and it can be incredibly useful in many scenarios. Next, there's the search operation. This lets us look for a specific value within our list. We can start from either the head or the tail and traverse the list until we find a node with the desired data. If we reach the end of the list without finding the value, we know that it's not present in the list. Lastly, we have the size operation. This gives us the number of nodes in our list. We can determine the size by starting at the head and traversing the list, counting each node until we reach the tail. Alternatively, we could keep track of the size as we add and remove nodes, incrementing or decrementing a counter as appropriate. Each of these operations plays a crucial role in the functionality of a doubly linked list. From adding and removing nodes, to searching for specific data, to simply figuring out how many nodes are in the list. Without these operations, our list would be much less useful. And there you have it: insertion, deletion, traversal, search and size. These are the primary operations you'll be working with when dealing with doubly linked lists. And with a good understanding of these operations, you're well on your way to becoming a master of linked lists. These operations provide the functionality that makes doubly linked lists so versatile. Everything has its pros and cons, and doubly linked lists are no exception. Let's dive into the advantages first. The primary advantage of a doubly linked list is the ability for bidirectional traversal. Unlike singly linked lists, which only allow you to move in one direction, doubly linked lists give you the freedom to traverse both forwards and backwards. This can be particularly useful in scenarios where you need to access elements from both ends of the list, or when you need to navigate back and forth within the list. Another major advantage is the efficient insertion and deletion of nodes. With a doubly linked list, you can add or remove nodes at both the beginning and the end of the list in constant time. That is, O(1) complexity. This is a significant improvement over some other data structures, where these operations might require linear time. However, it's not all sunshine and roses. There are a few disadvantages to keep in mind when considering the use of a doubly linked list. The main disadvantage is the extra memory overhead. Each node in a doubly linked list requires space for 2 pointers, one for the previous node and one for the next node, in addition to the data element. This is in contrast to singly linked lists, which only require space for 1 pointer per node. This extra memory requirement can add up, especially in cases where you're dealing with large lists. As a result, doubly linked lists may not be the best choice if memory usage is a key concern. In summary, doubly linked lists offer a lot of flexibility, with the ability to traverse in both directions and perform efficient insertions and deletions. However, this comes at the cost of increased memory usage. Therefore, when deciding whether to use a doubly linked list, it's important to weigh these advantages against the memory overhead and consider the specific needs of your application. While doubly linked lists provide more flexibility, they do come at the cost of increased memory usage. Now that we have a good understanding of doubly linked lists, it's time to see how we can implement one in Python. We'll start by defining a node class. Each node in a doubly linked list has 3 components: the data, a reference to the next node, and a reference to the previous node. So in our node class, we'll have an initializer method that sets these 3 components. Next, we'll create a doubly linked list class. This class will have a head and a tail, which will point to the first and last nodes of the list, respectively. In the initializer method for this class, we'll set both the head and tail to none, as the list is initially empty. Now, let's implement 2 methods for inserting data into our list, one at the beginning and one at the end. The insert@beginning method will create a new node with the given data and adjust the head and next references accordingly. If the list is empty, both the head and tail will point to this new node. Otherwise, the new node will become the new head of the list. Similarly, the insert@end method will add a new node at the end of the list. If the list is empty, this new node will be both the head and tail of the list. Otherwise, it will be added to the end, and the tail pointer will be updated. Finally, we'll implement 2 methods to display the list, one in the forward direction and one in the backward direction. The display forward method will start at the head of the list and follow the next pointers until it reaches the end of the list. The display backward method will do the opposite. It will start at the tail and follow the previous pointers until it reaches the head. So let's look at an example. We'll create a doubly linked list object, add some data to it using our insert@beginning and insert@end methods, and then display the list in both forward and backward directions. And there you have it, a simple implementation of a doubly linked list in Python. Output: